Alright, so today we have this problem that we have a wire of length 0.25 meters that is experiencing a uniform magnetic field that is directed north and has a magnitude of 0.05 teslas. We know the mass of the wire is 0.003 kilograms, and we're determined to find out how much current is flowing through the wire and what direction it's flowing in if the wire is in static equilibrium. Because since this wire is also experiencing a magnetic field, it's going to be floating. So we'll get to that in a minute. But for now, let's determine the direction that the current is flowing in the wire. So I think the first thing to note off is that we do need to introduce a third dimension, because when you take the cross products of two dimensions, it's going to give you the perpendicular vector in the third dimension. So when they say that the magnetic field is directed north, I'm going to call that into the board. And the reason I'm doing that is because if north is into the board, we can say that our force is going to be upward, because that's going to be opposing the gravitational force downward. So we know that force is up and B is into the board, so we can apply the right-hand rule to determine which direction that the current will be flowing in. So our thumb is going to point in the direction. Let's see if pointing to the right is correct. So we're going to take our right hand and point our thumb in the direction of the current. We're assuming we're going to check to see if right is the right direction. Point our pointer finger in the field, direction of the field, which is into the page. And then our force vector is going to be up. So this stays consistent. So this tells us that our current is going to the right, which is east. So that tells us the first part of our question, that the current is flowing to the right or to the east direction.
Okay, so now that we've established that the current is to the east, we have the direction, so now we can figure out how to solve for the actual magnitude of the current. So we have a useful formula here that is specifically for a wire of a certain length, which is IL cross B. So this is a cross product. This is why we were able to apply the right-hand rule. And this will allow us to solve for our magnitude of our current, because F and mg need to equal each other in order for it to be in static equilibrium. So, and how we'll be able to turn this from a cross product into actually solving for I, since the angle between B and L is 90 degrees, so B is perpendicular to L, we would rewrite this as ILB sine of theta. Theta is going to be 90 degrees, so it would be ILB sine of 90, and sine of 90 just goes to 1. So in order to solve for our current, we'll have our, so this gives our force up. So we'll have ILB times, sorry, it's an M. ILB times 1 is equal to mg, and then we can evaluate.
Finally, plugging in all of our values to solve for the magnitude of our current, we can just divide LB to the other side, get this out, and then plug in all of our values. So the mass of our wire, as previously mentioned, 0.003 kilograms, multiplied by 9.8 meters per second squared, which equals 0.294 newtons. And then we're going to have L, the length of our wire, which is 0.25 meters long, multiplied by the field. So we have 0.05 teslas equals 0.0125. Dividing the two of these numbers, we come out with our final answer. Our current is 2.35 amps.